Hello students, today topic is types of semiconductor and effect of temperature. In this session we will cover the following contents. We will briefly revise the core representation of the silicon and germanium atom. Then we will discuss the different types of the semiconductor. We will see that how the intrinsic semiconductor will behave at absolute temperature and room temperature. Similarly, for the extrinsic semiconductor, we will see both N-type and P-type semiconductor, how they behave at the absolute and room temperature. Also, we will see how the N-type and P-type semiconductors they are represented. So let's start with the core representation of silicon atom. Silicon and germanium are two semiconductor materials which are widely used for making the electronic devices that understand the core representation of for the both atoms. So this is the structure of the silicon atom. We have the 14 protons counterbalanced by these 14 electrons in the different three shells. Similarly, this is the structure of the germanium atom in which the 32 protons are counterbalanced by the electrons in the four shells. So what is common between these two structures is that both structures have four electrons in the outermost shell or the valence shell. So instead of representing the atom separately, we have the common core representation in which we include only the inner shells of the both atom, and this is how they are represented. This plus 4 charge showing the proton that we have the 4 proton in excess, which is counterbalanced by the 4 electrons in the outermost shell. So overall this atom is neutral. This is called as the core representation. Let's quickly revise the different types of semiconductor. There are two types of semiconductors. We have the intrinsic semiconductor and we have the extrinsic semiconductor. In intrinsic semiconductor, again there are two types, N-type semiconductor and the P-type extrinsic semiconductor. So let's start with the intrinsic semiconductor. So let's discuss the intrinsic semiconductor at absolute temperature. Intrinsic semiconductor is an undoped semiconductor. It is the purest form of the semiconductor as it has 1 parts of impurity per million silicon atoms. So at absolute zero temperature, the intrinsic semiconductor will behave as a perfect insulator. So let's understand, this is the silicon structure. We use the core representation studied in earlier slide. This is the each silicon atom shared their electrons with the adjacent silicon atom and made the covalent bond. Maximum electrons which can be accommodated in the valence shell is 8. So you can see these silicon atoms, they are tightly bound. There will be no free electron available in the structure at absolute temperature. So if we talk in terms of the energy band diagram, this is the energy band diagram of the intrinsic semiconductor. So you can see that all the electrons are tightly bound in the valence shell. So we have the valence, all this valence band is full of the electrons and there will be no free electron available in the conduction band. So right, so if the material is silicon, the energy required by these electrons to reach the conduction band is 1.1 electron volt, while in case of the germanium it is 0.72 electron volt. So we will conclude that at absolute temperature, the intrinsic semiconductor will behave as a perfect insulator. Let's discuss the intrinsic semiconductor at room temperature. This is the silicon structure at absolute zero where there is no free electrons available in the structure. But as the temperature is increased, it will break the few covalent bonds and generate free electrons. As soon as these free electrons are generated, it will leave behind a vacancy in the structure called as the hole. These electrons and holes which are generated in pairs due to the breaking of the covalent bond are called as the thermally generated electron hole pairs. If we make the energy band diagram at room temperature, few electrons which are available in the valence band, if we provide the external energy in terms of the heat or if we increase the temperature, few covalent bonds will break and these electrons will reach to the conduction band and leaving behind the hole and vacancy in the valence band. But the drawback of this intrinsic semiconductor is that the conductivity is not sufficiently increased. Why it is not increased? Because the number of electron hole pairs generated are very less in numbers. So we have not achieved a sufficient amount of conductivity. So we need to find some alternative way to increase the conductivity of the semiconductor. So the drawback of the intrinsic semiconductor is that on increasing the temperature, we have not achieved the sufficient amount of conductivity. That's why we cannot use the intrinsic semiconductor as a material for manufacturing the electronic devices. So we need to find some alternative way to increase the conductivity of the semiconductor. One way is doping. When we do doping in the semiconductor, we get the another category of semiconductor called as the extrinsic semiconductor. So doping is the process of addition of the impurity in order to increase the conductivity of the semiconductor. Note that the conductivity of the semiconductor can be controlled by controlling the amount of doping in the semiconductor. So we have the two types of extrinsic semiconductor. One is N-type extrinsic semiconductor, another is the P-type extrinsic semiconductor. So in the N-type extrinsic semiconductor, we use the group 15 element or pentavalent impurities, which has the 5 valence electron in the outermost orbit. And while in the p-type semiconductor, we use the group 13 element or the trivalent impurities. Why it is called trivalent? Because it has 3 valence electron in the outermost shell. So in N-type, we have used the material phosphorus, while in p-type semiconductor, we prefer the material boron for the doping process, right? So this is the core representation of the phosphorus, in which the 5 valence electrons, out of the 5 valence electrons, 4 are shared with the adjacent silicon atom and 1 is not shared with any silicon atom. Soon you will see that this will contribute to the conductivity. And while this is the core of the representation of the boron, in which this vacancy is showing that it is ready to accept 1 electron from the structure, right? Let's discuss the behavior of N-type extrinsic semiconductor at absolute temperature. To make the N-type extrinsic semiconductor, phosphorus atom is used as a doping material. This phosphorus is the pentavalent type impurity. The amount of doping is done in such a way that for every 10⁶ silicon atom, we added the 1 phosphorus impurity. So as soon as the phosphorus impurity is added into the silicon structure, it is surrounded by the silicon atom. Every phosphorus atom has 5 valence electrons in its orbit, out of which maximum 4 electrons will be shared with the adjacent silicon atom, leaving behind this 5th electron. This 5th electron is going to contribute in the conductivity significantly. As soon as this 5th electron will be loosely bound from this phosphorus atom, it will establish an energy level just below the conduction band called as the donor level. The energy difference between these conduction band and the donor level is so much less that it will be provided at the room temperature sufficiently. Note that at the absolute temperature, there will be no electron hole pair generation process, right? Let's discuss the behavior of the N-type extrinsic semiconductor at the room temperature. So at room temperature, you will see that the 5th electron will be loosely bound from this donor ion and leaving behind the positively charged phosphorus ion. So you can see as the temperature will be increased, this electron, 5th electron will be donated to the structure and it will become free, leaving behind the phosphorus atom as a positively charged ion or a donor ion. So why it is called donor ion? Because it donated 1 electron to the structure, it gives 1 free electron to the structure and become itself positively charged. So you can see in the energy band diagram also that this 5th electron, which is at the energy level, donor energy level, as soon as the temperature is increased, they will reach to the conduction band. Now, at the simultaneously, there will be a process of thermal generation of electron and hole pair at the room temperature. As you can see that we will get additional electron hole pairs. This is the thermal generation of the electron and hole pairs. So you can see in the valence band, as soon as the room temperature will be there, due to this, there will be a generation of additional reaching of the electron in the conduction band. So if we talk about the majority and minority, so in type semiconductor, we have the majority as the electron, which is a free electron available in the conduction band, and minority as a hole, which is in the valence band, right? Let's quickly understand the representation of the N-type semiconductor. So N-type semiconductor basically consists of 4 entities. One is the donated electrons, another is the phosphorus ions, and the another is the electrons due to the thermal generation process, that is electron hole pair generation process, and holes again due to the electron hole pair generation process or thermally generated holes, right? So this is how the representation is done. That this is a silicon semiconductor in which we have the donor phosphorus ion. Each donor ion has its own donated electron with it to neutralize it. And beside this is showing that electron hole pairs are generated. So for every electron, there is a hole is there. So completely this structure is neutral, right? So this is the correct definition for these charge carriers. So overall, the majority charge carriers are in the N-type semiconductor are electrons, and minority charge carriers are the holes. And these are the immobile positively charged ions, which will contribute, which will useful in forming the dipoles. So let's discuss the behavior of p-type extrinsic semiconductor at the absolute temperature. To make the p-type extrinsic semiconductor, we use the trivalent impurity. For boron is used as an impurity atom. For every 10⁶ silicon atom, one boron impurity is added into the p-type semiconductor. So in the silicon structure, this boron type impurity is surrounded by the silicon atom. So as soon as the boron atom is added, boron has a 3 electron maximum available in the valence shell. So maximum it can share its 3 electron with the 3 silicon atom, leaving behind the 4th silicon atom without any bonding. Right. So this will create a deficiency in the structure, or we call it as a vacancy in the structure, which is ready to accept the electron from the structure. This type of impurity is called as the acceptor type impurity. Right. So we called it is that the hole is created in the structure, means it can accept the electron as soon as the energy will be provided, as soon as the temperature will be increased. This will has the tendency to detach the electron from the adjacent silicon atom. We will see in the next slide, and we will see it will become the negatively charged ion. Right. So and in the energy band diagram, we will see that these vacancies are at the hypothetical level called energy level called acceptor level. So they will have the higher energy to detach the electron from the valence band, which you will see in the next slide. Right. So let's discuss the behavior of the p-type extrinsic semiconductor at room temperature. So at room temperature, you will see that we have the boron atom in the structure, which makes the covalent bond with the 3 adjacent silicon atom, and it will give one hole to the structure. This hole, which is created due to deficiency of the electron, will give the hole to the structure, which has the higher tendency to snatch out the electron. So as the temperature will be increased, it will snatch out the electron from the adjacent atom and transfer the hole to the new position, that is the new hole is created. So as the electron is transferred, it is a deficiency of the hole is nothing, it is a deficiency of the electron. So we can say this is a positively charged carrier, although the electron is moved, but we will think it as a positively charged carrier movement, right? So you can see that as soon as the boron atom will accept the electron from the structure, it will become negatively charged boron ion, or it is also called as the acceptor immobile ions. So in energy band diagram, these holes, boron holes, will be at the acceptor level. These are the electrons due to the silicon atom. So before understanding it, at the room temperature, the process of thermal generated electron hole pair will be conducted. So this I have shown here, that as soon as the temperature is increased, or semiconductor is kept at the room temperature, the electron hole pair is generated. So this process is shown here also, that if the temperature is given, the electron will reach to the conduction band, leaving behind the hole in the valence band. So now what will happen to these holes which are at the acceptor level? They have the higher tendency to snatch out the electron from the silicon atom. As the temperature will be increased, they snatch out the electron from the valence band of this adjacent silicon atom and leave behind the holes in the valence band. So you can see that in the p-type semiconductor, the majority charge carriers are the holes and minority charge carriers are electrons, and we have the immobile charge carriers as negatively charged things. Right. So how the p-type semiconductors are represented? So let's discuss it. In this structure, we have the one vacancy is shown here. That there is a one hole which is created due to this boron impurity, and after accepting it as a one electron from this structure, boron will become negatively charged acceptor ion or immobile ions, and it will give one hole to the structure, right? So this, and again parallelly there will be a electron hole pair generation due to the increase in temperature due to the breaking of the covalent bond. So we get this hole and electron also due to the thermal generation. So this is how the p-type semiconductor is represented. In the p-type semiconductor, we have the electron and holes this is the electron hole pair. So we have the again four types of impurities we have. We have the holes corresponding to each boron atom, and we have the immobile negatively charged boron ion. We have the thermally generated negatively charged electrons and thermally generated holes positively charged mobile carrier, which is generated due to the heat, and they are very less in numbers, right? So the majority charge carrier in p-type semiconductors are holes, and the minority charge carrier in the p-type semiconductors are the electrons. And besides these majority and minority, we have the negatively charged boron ion, which will help to form the dipoles. So this is all about this session. Thank you very much.